everybody, and welcome to our webinar today. We are going to talk about oxygen power basic analysis function. And so we're going to talk about our software and how to do basic analysis and how to use oxygen in this kind. But before we start, I would like to explain, as usual, some organizational things to allow other people to log in, because I still see that people are trying to log in. So on your right side of your webinar tool, you can see a chat. This chat is used so that you can ask us questions. Those questions are anonymous. Only me and my colleague can see them, and we are going to answer them if possible during the webinar or at the end of the webinar. Please use this opportunity. We are live now, so you, as I said, use this opportunity. We will answer those questions, as I said, during the webinar, and there are also handouts available for download also on your right side during the webinar. Use also those handouts and downloads. So that's so far. I see most of the people are connected and are logged in. So let's start. Today, I'm going to be your moderator. My name is Ivica Baresic. I'm sales and business developer for Austria. And I'm joined by my wonderful colleague, Verena Niederkofler, know-how expert and application engineer at Devitron. Hello, Verena.
Hi.
Do you want to introduce yourself?
I think you already said the most important things, so.
Okay. Perfect. Okay. So it's a pleasure to have you on the show today and on this webinar today. And yet, I think we should start already with the very first question, Verena, for you today. And that would be like, typically, there is a necessity to measure power between three phases, so a typical three-phase power measurement. Can you show us how this is realized or how this is done with oxygen?
Yes, so I have set up a small demo motor next to me with a power analyzer, and I would just like to explain you the differences between two different configurations. So the first one is the delta configuration. That's the one I set up here with the motor, where we measure the voltages between the phases. So we connect the phases in a way like this. And we also measure the currents directly with our submodules here. Then we have, so that's our three-phase system here connected to the motor. And then we have a one-phase system on the net or the inverter side, which we also connected to the power module. So the advantage here is that we don't need the neutral line from the motor. So we have a three-phase, three-wire configuration. The other configuration is the star configuration. So where we have a virtual star point, which we set up here. So we just connect those three channels. And this virtual star point, we connect to the neutral line of the motor. Sometimes the neutral line of the motor is not accessible, and therefore the virtual star point here could float. So if it's not accessible, it might be better to connect it in a delta configuration. Yeah, so like I already said, we set up the motor in a delta configuration here, since with the small motor here, the neutral line is not accessible. And these are the small differences between those two configuration types.
Perfect. That's how you connect. So that's how you connect a three-phase motor to a power group of Devitron, or to a power module of Devitron. In our example, our motor is very small, so we connected it, or we measured the current directly with our direct current input. So that's a special that's special for Devitron. We have direct current input, so that's a huge benefit compared to other power analyzers. And in most cases in industry, we have to measure 100 of amps, and therefore we would need current transducers. How do you use current transducers within oxygen?
So like you already said, since this is a real small motor and we don't have a lot of current, we measure it directly, but a lot of applications need current transducers. So whenever a current transducer is connected, I will just open the channel menu, so the data channel list. And here I can already see these are my 3 or 4 channels for the current. So whenever we have a current transducer, I would like to show you an example. So for example, the LEM EN500S current transducer. I opened the data sheet, which you can download on your website. And the scaling factor we need is usually here. So that is the number of secondary turns. Sometimes it's also called conversion ratio. So we need this scaling factor to put in the software to scale the current in the right way. So I will just minimize this, and that's so we can either do it here, right here in channel settings, or we open the channel setup menu, and here we have our scaling information, and here we just change the factor to 750. And that's actually it. So we have scaled our channel, our current channel. Here you already also see our scaling factor, and that's how you simply set up your current channels in the right way if you use a current transducer.
Mm-hmm. So in most cases, you use the same transducer multiple times, and do we have to do these changes for every single channel all the time, or is there a shortcut?
There is a shortcut, or more ways to do it actually. So you can either enter the scaling factor 1 and then copy paste it to the other channels, or you can also go into your system settings and use our sensor database here. So as you can already see, it's just one current transducer in the list, but you can simply add new sensors here. For example, let's add another one, the 1000S. It has an input type, also current. I don't know the scaling factor right now. Let's just say 1500. And here you can set up all your current sensors which you are using. If there's different sensors, you can just set it up in here. It will be saved as an XML file, a sensor database. You can also use it for other systems. Just copy the XML file and use it on another Davatron system. And the way how you use these sensors in your channels is the following. So let's say we have here our second current channel. We open the setup menu again. And up here you see the button choose sensor. So whenever we click it, we get this small pop-up window with the whole list of all the sensors we set up previously. You can use the search field or just choose the sensors you would like. And then just click OK. And as you see, the scaling factor change and also the other settings which are saved in the sensor would be changed here. You can see the name of the sensor up here and also down here below. It's a little bit small. I hope you can see it. So that you already know quickly that you have used a sensor. And the other nice thing is if you have connected a sensor and you use the sensor database, you can also see it up here in the overview picture that on the third channel here, you have or you are using a sensor. And if you go over it, you can also see the name. So it's a really nice and easy way to use it.
Perfect. So we have the sensor database, but we should also not forget about the copy and paste function. So if you set up a channel, you can easily copy and paste it to a different channel if needed. So you don't have to do it all the time manual, which is drastically reducing the possibility of error if you set up a new measurement. So yeah. Within oxygen, we talk very often about power groups. So can you explain to everybody watching what a power group is and what it is used for?
Sure. So a power group within oxygen is like a calculation group for which calculates all the different power parameters of the selected current and voltage channels. So it's not, a power group is not predefined within oxygen, but you can set it up yourself with different number of phases and different numbers of power groups also. You can have different power groups with a different number of bases within oxygen. So for example, you can have one three-phase power group where all the power parameters are calculated for these three phases. And then you can have another one-phase power group where all the same power parameters are calculated automatically within oxygen. So it's like a calculation group where all the different power parameters are calculated. Just how we define a power group within oxygen.
Okay, so that's like a motor is like a power group, or a one-phase grid is a power group. So things that you have to combine to make the overall power consumption or energy consumption. Can you show us how such a power group is made within oxygen?
Yeah, sure. Let me just delete the scaling factor since we are not using it.
Yeah.
Otherwise, we will not measure it correctly.
Yeah.
Okay,
Yeah.
so there's two ways to set up a power group. So the longer way would be to click on the plus, and then we select the power group here in the list and click on add. And we already see here our power group setup, where we select with the different selections of wiring types, where we can select the right wiring type we are using, for example, for our one-phase system on the inverter side. And then we just simply drag and drop the voltage and the current channel into our wiring type in our schematic here. We can already see a small preview where we can already see if we measure the correct thing. Sometimes for the motor, it's nice to see if we have connected, like if you use current clamps, sometimes you have it connected the wrong way, so the power is negative for something, and then here you can already see it very nicely if everything looks fine. Here we can also change the name so we can better find it afterwards.
So just to explain, Verena, so we are doing a live measurement. You have a motor kit next to you. It's a small motor kit, but we have a power analyzer connected to it right now. We are already measuring the power grid here in Austria, which is 230 volt and 50 hertz. So this is also perfectly fine. Just to explain, I think we didn't explain the application. So we do have a real motor next to you, and you're going to turn it on, and we are going to do a live power basic measurement on that motor.
Yes,
correct.
Perfect. Okay, so that is the first way to set it up. The other way, the faster way to set it up is to select the voltage and then the current channel for each phase individually. And it's important to first select the voltage channel. So that would be the first phase, the second phase, and the third phase. And then we simply click on this button here. And we already see the power group is set up automatically. Here we just have to find or choose the right schematic or see if it's the right one. Here it automatically selected the three-phase 4-wire, but we are using the three-phase 3-wire. I'm just gonna turn on the motor now. And now we can already see some values which look correct. So it's a really small motor, but they look fine. If we messed up the selection here, we can also simply change channels by drag and dropping in here. So that would also work. We don't have to delete everything and then like set up everything again. And then we just rename
by a quick order of your channels, the power group knew which is the current, which is the voltage, and it automatically filled out those 6 fields in the power group.
Yes, it's just important to select the voltage channel first. Otherwise, they will be mixed up here, of course. But if you know, then it's really easy to set it up. You just select all the voltage and current channels for each phase individually, and then just simply click that button, and then you have to just select the schematic if for the wiring type if it has chosen the wrong one.
Mm-hmm. Okay,
Um,
perfect.
okay, so that would actually be it for setting up the power group. It's really simple, really
Yeah,
easy to do. And
yeah.
just to show you real quickly the parameters which are calculated, maybe we have a lot of different parameters. I'm for sure not going to go over each one since that would be too much for today. But as you can see, we have already the fundamental frequency, we have the voltage, the RMS values. Actually, we can also fill out this little schematic I prepared so you can have a small overview of
Mm-hmm.
the parameters. So here we have the first power group, the voltage, and as you can see, there's a lot of different parameters which are calculated automatically
Mm-hmm.
in the power, and then we open the motor
Yeah.
power group, and as you can
So,
see, please,
so
sorry.
yeah, so with the 5-6 clicks that you did for the power groups, you get a lot of values which are calculated automatically.
Yes. Yeah, so there's many values in there.
Mm-hmm.
And as you could already see, we measure in a delta configuration, we measure the phase pace voltages, but the software automatically also calculates the phase line voltages.
Mm-hmm.
So it's there's no difference in what way we have connected our measurement system.
Perfectly. So even if we are connected in Delta and we are measuring line to line, we are generating a virtual start point and we are calculating the phase voltage by itself. Perfect. Mm-hmm.
Yeah. So as you can see, a lot of different parameters. So this is just for a small overview of all parameters which are calculated. Here we also see the
Mm-hmm.
fundamental frequency. If I change it, you can already also see it changing.
Yeah. So we are live measuring and we see already like a schematic here what we are measuring and we see the most important values as well. In real application, it's very necessary or it's necessary in the most points to combine two different power groups like the power group the grid and the power group motor, for example, to calculate the efficiency of the inverter. So how do we calculate the efficiency? How do we connect those two power groups? How do we calculate the efficiency of the motor, of
Mhm.
the converter? Sorry, for example.
So that is also not that much work. So we just open the
Mhm.
channel settings again. I will add a formula by clicking on the plus. I choose the formula and click on add. Now I
Mhm.
have a new section for a formula. And
Mhm.
to calculate the efficiency, I need the power of both power groups, the total power. I just use the search field to get the right channels here of both
Mhm.
power groups. And then I simply choose those power or those channels and
Mhm.
use the fields here. And I would like to have a percentage value, and I can here also rename my formula. That's it.
Mhm.
So we already have our efficiency calculated like this. I will just close this and also drag and drop this efficiency formula onto my
Mhm.
overview. So yeah, that's it. Really,
That's
really fast.
that's really fast and easy, and it is just a short glimpse on the math possibilities of Devitron and of oxygen, of course. It's so much more possible, but it's just to show you like a short glimpse to the mathematic options that are available within oxygen. And that math library is just huge, and we just showed like basic algorithms, but yeah, that should be mentioned as well. So yes, we can easily combine the values that are generated by two different power groups and make a math formula out of it and do, for example, the efficiency of the frequency converter. This is perfect. So this screen was made by yourself now while we talk, and we should highlight that within 20 minutes, while I talk as well a lot, we made a complete measurement of two complete different power groups and even the efficiency. So within 20 minutes, we have been ready to start the measurement. But in some applications or in some praxis test, you have to be faster. Is there a way to show the most important power values way faster than like drag and dropping every single field out of the
Of
power group?
course, of course. So let me just make another screen here. So of course, there's a simpler way to do that. So this is an empty screen, and to get an overview of the most important values, I just simply grab my power group and drop it on my screen. So if I make it a little bit larger, you can already see here are the most important values of this power group. I cannot change this table here, but I don't think it's necessary. If I need other values, I can also use other instruments like the digital meter to also show on my screen, or I make like my own table, which is also fine. Here in this instrument, it has a nice feature. So I can also switch the view with this button here, and I get all the phase relations between current and voltage shown with these diagrams. Yeah, so this is the fast way of the table. So it's just one click actually.
So to visualize very fast, we have those predefined tables of the power groups, and as you see, the most important values are available here. We already got a question regarding the calculations of the power group, and the question would be, I hope you can answer it. Do we calculate the displacement power factor?
Yeah, so that's a good question. Like you already saw maybe before, we sometimes or we usually have these two sections in the calculations, in the parameters. So we have the total and the fundamental. The total means all frequencies are considered in the calculation, and fundamental, only the fundamental frequencies, only the frequency which is calculated here is considered in the calculation. So the displacement power factor is the power factor of the fundamental frequency, so only the fundamental frequency between current and voltage. So yes, we do calculate it, and you can just find it here where the fund ending is added to the power factor.
Okay.
The
I didn't
other
know it
one
called
we
like
have
that. Okay.
it's here for total,
Okay.
but for the displacement power factor, it would be the fund here.
Okay, perfect.
Yeah.
So that's about like basics, and that's also like the oxygen basic, and we're going to do some little bit, we're going to go deeper. I would like to go into theory a little bit. Can you tell us how the power values are calculated within oxygen? What is so special about the Davidson power analyzer?
Okay, so to show you, I also have this picture here, which gives a little bit more insight. So we calculate every value for each period. So we don't have like a fixed time window where we calculate the parameters, because then the periods might get cut off, and the values would not be calculated correctly. So we have the zero cross algorithm, where we detect each positive zero cross from each period. So here you would see for each line here, the zero cross, a positive zero cross is detected, and each power parameter is calculated at this point. Whenever the fundamental frequency of this signal source is below a certain threshold, which is like 0.2%, or the fundamental frequency cannot be detected anymore, then it will switch to an interval mode where we have a time window which is between 50 and 100 milliseconds, depending on the sample rate, where the power parameters are calculated until the first positive zero cross is detected again. So as you see here, the signal comes back, and here the first positive zero cross is detected again. So therefore, we have, after this first period again, we have the calculation, which comes back automatically. So I don't need to do anything. So this is how the power parameters are calculated within oxygen.
So this is valid for a fundamental frequency up to 1 kilohertz. So for up to 1 kilohertz fundamental frequency, we calculate for each period a single value. If I'm not on, yeah, exactly.
We can detect the fundamental frequency in a range between 0.2 hertz up to 200 kilohertz. So this is the range of fundamental frequency we can detect, and we can also calculate the power parameters.
Perfect. So also for different for motor, if you have to start up a motor, it's done completely dynamic. It's done completely automatically. There is nothing to change. You have not to worry about having any correct calculations. They are going to be correct all the time, also for a run-up.
Yeah, so this is a small insight. If someone is interested in more details, there's a more detailed description in the power manual, or you can just let us know. We can talk about it.
It's just a little bit about theory and how our power analyzer works. And is it possible for you to show us the calculated values in a recorder? Because we are a recorder as well. We can record raw data. And in this graph that you showed, it's a nice sinus. And of course, with a sinus, you have wonderful positive flanks, you know. But at the frequency converter, the signals don't look that nice. And could we show our viewers that we hit those positive and periods, even if the signal doesn't look very nice, very accurate?
So I will use the first voltage channel here, which is used for the calculation of the fundamental frequency. And then I will just add fundamental frequency maybe and the power to have like two different parameters of the power. So I will just zoom in a little bit and freeze my screen, otherwise we cannot see anything. Maybe I have to change the color so you can see it better.
Yes. Yeah, I can see it.
That's that better? No?
Yes, it is definitely.
Okay. Okay, so I will zoom in a little bit. So as you can see, I hope you can see it, the small dots here. Let's zoom in a little bit more.
Yeah, you have to look very exactly, but you see a dot there, yeah.
So here, this is the power parameters, which are calculated like here, after each period.
Perfect.
This is one period. We can also use the cursors and set it to this point and to this point. So right now we have a fundamental frequency of 60 hertz, and time window is exactly 16 milliseconds. Can also switch the frequency for the cursors. So you can see it a little bit better. So here are the 60 hertz. I can find exactly.
Yeah.
So that's the 60 hertz. If I change the frequency, of course, it will also change automatically. So I will just maybe go to 50 hertz here. Okay, that's good enough. Oops. Then we freeze the screen again, turn on the cursors, and as you can see here, I put it to this point and here, so that will be exactly one period, and now we have the 50 hertz. So it will adjust the frequency or the period, the calculation accordingly to the fundamental frequency.
So we are doing this for every period in high dynamic, fast run-ups. This is done automatically. We are going to have always correct electrotechnical power calculations. They're always going to be correct. You don't have to bother around if you have a fast run up that your window size may be different and that your frequency is going to be out of this window size and that you don't have a full period in the window size. So you don't have to bother. This is done completely automatically by Oxygen, and which is making, of course, the work with the power analyzer so much easier. Perfect. Which channel, or let's say that way, the fundamental frequency is very important to calculate power, of course, and you have to synchronize on one channel to get the fundamental frequency. On which channel do we do this kind of synchronization?
Okay, so as I already showed you before, I use the first voltage channel of my motor power group. Since I told you this is used for this calculation of the fundamental frequency. So per default is always the first channel for the power group. If I just open the settings, it is always the first voltage channel of the power group per default, which is, you can see the green background, so I can see this channel is used to calculate the fundamental frequency and therefore to give like the period interval for the calculations. If I change the power group here, I also see, well, we only have one voltage channel, but it's also the voltage channel here. If I would like to use another voltage channel or also current channel, I can just enter the settings here, and I can see here for the calculation sync source input channel. So this is the U1, the first voltage channel. If I want to use the second one, I can just simply drag and drop it in here and use another channel. Usually we say that people should not change anything in here since the settings are done in a way that it should work for like 99% of the applications, unless you really know what to do. Then you can change something in here, but usually it should just be left like this. But for some applications, it might be needed to change the synchronization source in here.
And as you mentioned, it's also possible to use current in case, you know, a shortcut is being measured where like basically there is no voltage. Current could be used to synchronize as well, or to
it could be
calculate the
used
frequency.
here also. Simply drag and drop it in here, and then this current channel would be used as a synchronization source.
And it's shown in the wiring type, it's shown like with a green background on which channel is being synchronized.
Yes, so now I chose the first current channel, and now this has a green background in here. Yeah.
Perfect. In a lot of applications wherein a long time measurement is always asked, so customers, because we do have this possibility to record raw data, they mostly use it when a trigger happens. So what they want to do is like record those power values out of the power groups like continuous, but the raw data not, because recording 2 or even 10 mega samples like for a longer time is going to explode your data file. So they would like to use a trigger to record raw data, but the power data should be recorded continuously. Do we have that possibility? Of course, I'm asking you because we do have it. So can you show us how this is done?
Of course. Like I already said, yes, this is possible. Yeah. So I'm just gonna open the triggered event menu, since we're gonna switch from a continuous recording to an event-based recording, since we just want to record the raw data for certain events or for a certain event. So we're gonna switch the mode here to event-based. We can set a pre-time. For example, let's set it to 1 second. So we also record like 1 second before the event actually happens. We record 1 second before, so we can see what happened before the event actually happens. And that might help a lot for the analysis. Here you can also see in a picture, so here the event would be activated or would happen, and that we also record this 1 second before the full raw data with full sample rate, which might help in the analysis. Here we also have statistics data, which is recorded as a background information for each channel, which is not so important for right now. The window is like 1 second, which is the minimum, maximum, average, and RMS value for each channel. We'll just leave this enabled since it doesn't take pretty much no data on the hard disk. So the next thing we need to do, we need to add the event. So we need to define when do we want the raw data or the channels which should be sampled with full sample rate, when should they be recorded also. So let's say we want to record our raw data here whenever the fundamental frequency goes out a certain window. So let's set a window from 45 to 55 Hertz. As you can see here, this bar is gray, so we are within this window right now. We are at 50 Hertz. If I just make it a little bit higher, the frequency, you can see it turns red. So the event works. Just turn it down a little bit again. So this is just to make sure that I set the event right or in a correct way. And then for the action, we just need to set it to record event. And that's it for the event. And the other thing we need to do is to set the individual channel configuration here. We activate it. So here we say that we just want to record the power parameters continuously and the other raw data just whenever the event happens. So we select efficiency and the power parameter, power groups, and select or change the waveform mode from default to continuous. So that is actually it. So continuous means this event will just be ignored. For those channels, they will be always be recorded, no matter if the event happens or not. For these channels, they have their waveform mode on default, so this means they are dependent on the event. They will not be recorded unless the event happens. Okay, so let's just return to our screen. Make a small measurement to show you. Okay, so I'm just going to arm a trigger and then set the frequency to different values, which you can also see in this digital meter. Okay, now we are within the window, get out of the window, and again within. Okay, so let's stop and look at the measurement file. Okay, what you can see here is all the statistics data I mentioned before. That's why I mentioned it. We're just going to hide it, so it makes more sense to look at the data.
Yeah.
Okay, so as you can see, there's some gaps in between. And if we go to the beginning and get our time cursor, you can see if we zoom in here and maybe also activate the cursors real quickly. And calculate the difference, the time difference between here, almost. It's not exact on the dots, but almost.
Yeah.
Okay, so we have the 55 Hertz and the 55 Hertz, which we measure also, which we already also set here. So we are within the time window we set. If we come to this point, we leave the window and we also record the raw data.
Exactly. So that's just an example of how a trigger could look like. So if the frequency is below 45 or above 55 Hertz, where maybe should not be, we can trigger and have the raw data recorded because something happened that we did not expect or that we wouldn't like to see, yeah.
So as you can see here, this is also within the window, but we set the pre-trigger, the pre-time
Yeah.
of 1 second. That's why we are still within this frequency window. So the actual trigger happens here whenever we left the 45 hertz.
Yeah.
And we set the pre-trigger of 1 second, so we also record the 1 second before in case something happened before, and we can also analyze this.
Yeah, it's very important because pre-time, we set it up to 1 second. It's possible up to 10 seconds. We should mention that one as well, because even if the trigger happens because of the voltage dropping or whatever, the actual incident could happen already like a couple of seconds prior to that, and you would like to see what happened prior to the real trigger. And that's very important, and that's very nice to have a raw data recorder even 10 seconds prior to the trigger you set. In a lot of cases, this is very, very necessary to have. Perfect.
Yeah. So as you can see here, we entered the window, the frequency window again, and the same thing happens here. So the actual trigger happens here whenever we leave the 55 hertz, and this is the pre-time of 1 second. And this is how you set up, like, to get a measurement for a long time measurement, where you can save a lot of disk space in case you sample with a really high sample rate, and in case you really need to measure for a longer period of time.
Okay, perfect. Let's go back again a little bit towards theory. Can you tell us some things, or can you show us anything about the accuracy and the calculations about it?
Yeah, so sometimes we get questions about accuracy calculations for specific points, and I prepared a small, can you see this now?
Yes.
Okay, so I prepared a small example where I just show you how like a calculation of the accuracy could be done. So we take again the EN 500S just for an example. This is a screenshot from the website where we can see the accuracy here, so the 0.0018%. And I also copied the specifications of the current and voltage input from our data sheets in here. So this would be the voltage input, and the current submodule accordingly, the 1 ampere submodule accordingly to this current transducer, since it has a output of 600 milliampere. And so we remember this value, let's say between, we take this first one between 0.0 to 1 kilohertz, the 0.03% of reading, and the same would be for also for up to 10 kilohertz here, for the same for the current submodule. Okay, so here I prepared some small calculations, which I will just go over real quick. So we have here again as a summary the voltage and the current input for the range. So the reading error, the 0.03, and we don't have a range error in this calculation. For the LEM current transducer, this was the 0.0018% of range error. It doesn't have a reading error. And here we can just define 2 points. So this is just like made up numbers. Here we calculate the power, and within these 3 fields, I calculated the reading and the range error for the voltage input and the current input, and also the current sensor. Since it's always important to also consider the current sensor, so that because it might have a great impact in the accuracy. So this is just the voltage times the reading error, the same for the range error, the voltage times the range error, and here the same for the current input and the current sensors with the according values. Here again, I calculated the power with all the arrows. So this is just the sum of all the voltages times the sum of all the currents plus arrows. And here we can just calculate then the total power error, which would be 0.062% at this certain point. So that is actually really easy. You can find all the specifications in the data sheets. The one thing to consider is these calculations can be applied for a power factor of 1. If the power factor plays an important role, which you also need to consider in the calculations, this is not a problem. We are very transparent for all our specifications. You can also find the influence of the power factor within our data sheet. So I just copied this from our data sheet. I specified the 50, like the hertz, the frequency, and for example, a power factor of 0.8. So here again, I calculate the power with the influence of the power factor. So this would just be the same calculation than this one with the influence of the power factor. So this is the power factor arrow. So this formula is exactly this formula down here, like in the data sheet. And then just the sum of those two, and this again is the total power arrow, which here would be 0.069%. So this is just a small example how calculations, accuracy calculations can be done for specific points if it's necessary.
Perfect. Thank you, Verena. So thank you for all your insights at this webinar. We are already at the end of the webinar, and there are so far no questions I can see in our tool. To everybody who is now watching, this webinar is going to be online on YouTube as well. If you have colleagues who would like to see this webinar, and if you know they could be interested in this webinar, let them know. We are going to put this webinar online, I think at the end of this week or beginning next week, somewhere in this around. So this webinar can be rewatched. If you have any further questions, feel free to contact me and my colleagues. Our contact data are available on our homepage and on social media, of course. If you know colleagues who could be interested in power advanced features, those webinars are going to take place next week, Tuesday and Thursday, if I'm not mistaken. I think Raphael is going to join me.
Yes.
Yes. Okay. So power advanced webinars are going to take place next week, Tuesday and Thursday. And the only thing to say now is thank you for watching. See you next time. And if you have time, stay online for 1 or 2 minutes to answer 1 or 2 questions to give us a feedback on how to improve our webinars. So again, thank you for watching and see you next time. Bye-bye.
Thank you. Bye.